on the Module 12 overview. This is the last chapter in segment 2, and it's kind of a short chapter. We just are covering limits, which are some basic concepts that you'll also see in calculus. The first thing that we're going to go over today is finding the limits. There's 3 different methods that you learn, which include graphing, looking at tables, and looking at algebraic methods. Okay, tables are also known as numerical or analytical. We're going to look at one-sided limits, meaning looking at the limit from the left and the right side. And then the last part is the 3 conditions of continuity. We're going to look at those 3 conditions as well as removable and non-removable continuity. Okay, so I'm going to go over a couple examples. The first thing that we're going to look at is finding the limit. Okay, analytically, which is also looking at a table, and then we're going to look at graphing. Okay. So if we look at the table that's provided, and say we wanted to find the limit as x approaches 4. We're going to look at our x value of 4, and this table is set up nicely because it includes all the x values leading to 4 from both directions, meaning from the negative side and from the positive side. When I look at those values, I want to know what is my y value approaching. If I look from the left-handed side, it looks like my y value is approaching 2. Okay, it's getting closer and closer to 2. I look from the right, it also looks like it's approaching 2. So my limit for this function is 2. Now, one thing to be careful of is make sure that your signs are the same. And in this case, they are positive. Positive 1.9 leading to 2, and a positive 2.1 leading to 2. Okay, if they differ from the left and the right, then we would say the limit does not exist. Okay, next we want to look at a graph to be able to identify a limit. Now, there's a lot of different places that I can find the limit here. Let's look at a couple examples. Let's look at the limit as x approaches 1. So here's my x value of 1, and I want to look at the y value. Now, from the left, it looks like my y value would be -1. From the right, the function is approaching 2. Since the limits from the left and the right are not the same, then we say the function's limit at x equals, or as x approaches 1, does not exist. Okay, let's go over another example, and I'm going to just erase what we did here so you can see the graph a little better. Okay, let's look at the function's limit as x approaches 3. So here's my x value of 3. Now I'm looking at the limit. The function is approaching -2. And I know I have a point up here. That's the function value. Okay, but that's not what the function is approaching. And we're going to look at this with continuity. But the function value and the limit don't have to be the same thing, okay, for the limit to exist. Now let's look at the limit from the right. It's also approaching -2. So for the limit as x approaches 3, it's going to equal -2 because the left and the right side both approach -2. Okay, so hopefully the graph, the 2 examples that I've shown you, gives you a good example of what to look for. The next thing that we're going to look at is finding limits algebraically. And I have a couple of examples, okay? But what we're going to do is we're going to plug in the x value, okay, and see if we can find the y value. Okay, if we can, then we know what the limit is. Okay. If we can't, we might have to do a little bit of work. So if the denominator is 0 and cannot cancel, then we would say the limit does not exist, or it's undefined. So I have a couple of examples here. The first one is the limit as x approaches 3 of x squared minus 9 over x minus 3. Now before we plug in to this function, we want to see if we can factor and cancel that denominator, because I can already see that my denominator would be 0. Let's see if we can factor the numerator. We can. And when we factor it, it actually cancels our denominator, which means there's just a hole there. Okay, and we can still find the limit. We just plug in the 3. We get 3 plus 3, which is 6. So the limit as x approaches 3 is equal to 6. Let's try another example. Let's try the limit as x approaches 3 of x plus 3 over x minus 3. Now, I can't cancel anything here, so I'm going to have to plug in the 3 to the numerator and the denominator. When I plug into the numerator, I get 3 plus 3, which is 6. But when I plug into the denominator, I get 0. And we know from Algebra 2 that if we have a 0 in the denominator, that the function is undefined. That also means that the limit is undefined, or it does not exist. Let's look at another example. Look at the limit as x approaches 2, and our function is x squared minus 3x plus 5. Here I'm just going to plug in. I don't have a fraction, so I don't have to worry about trying to cancel. I'm just going to plug in each time I see an x. We have 2 squared minus 3 times 2 plus 5. So 4 minus 6 plus 5. So negative 2 plus 5, which gives me a positive 3. So the limit as x approaches 2 is equal to 3. So we can find our limits. We could have also graphed these or looked at a table, or we can plug into the function. So those are your 3 different methods for finding a limit. Next, let's move on to finding a limit, a one-sided limit, meaning finding a limit from either the left or the right side. Now, I can see that the PowerPoint, it's not very dark, but when the limit, when they're asking you to find the limit from the left, there's going to be a little negative sign above that C. So it's going to look like the limit as x approaches some number and then a minus sign. It looks like the exponent of it. For the limit from the right, we're going to have a little plus sign. Okay, now we can have a one-sided limit, but in order to find the limit, the true limit, where it's just limit as x approaches C, the left and the right-hand side limits have to be the same. Okay, and then when we look at piecewise functions, and I'll give you an example. Okay, you plug in based on the domain. Okay, so if it's from the left, you want to find the domain, okay, where it's less than that C value, and to find the limit from the right where it's greater than. And it can also be when x is less than or equal to C, or x is greater than or equal to C. And a couple of the examples will help explain this. So let's look at a graph first. And our graph, just draw. And we're going by ones here on our graph. Positive 1. This is a positive 2 and a positive 3. Okay, let's look at the limit as x approaches 1 from the left, the limit as x approaches 1 from the right, and the limit as x approaches 1. So from the left, okay, we're going to trace the graph and look, and I see that my y value is approaching 1. So the limit from the left is 1. When I look at the right, I trace the function, and the limit, the y value that it's approaching from the right is 2. Okay, so we have a left-sided limit of 1. The right-sided limit is 2. But the overall limit as x approaches 1 does not exist, because 1 is not equal to 2. So you can look at the graph and identify if we have a one-sided limit. Next, I'm going to show you a piecewise function, so having an equation and finding one-sided limit. So our function here is f of x equals, we'll do three pieces, x minus 2 when x is less than 0, x, the function value is x when it's between 0 and 2, and the function is equal to x squared when we're looking at values that are greater than 2. So let's find a couple different limits. Let's first find the limit as x approaches 0 from the left, the limit as x approaches 0 from the right, and the limit as x approaches 0. And then we'll look at another example. Okay, so let's look at the limit as x approaches 0 from the left, meaning that if the c is 0, we're looking for the domain, and here's your domain column, when x is less than or equal to 0, which looks like this first equation. So I'm going to plug in, and I get negative 2. Now from the right, I want to know when x is greater than or equal to 0, which is right here. Okay, when I plug in 0, I get 0. So I have a left-sided limit and I have a right-sided limit, but the overall limit does not exist because negative 2 does not equal 0. Let's look at another example, and I'll write it up here in red. Let's look at the limit as x approaches 2 from the left, the limit as x approaches 2 from the right, and the overall limit as x approaches 2. Same thing here, we're going to look at when x is less than 2 for the limit from the left. So that would be the second equation here, which is just plain old x, plugging in x 2. Now the limit from the right, when x is greater than 2, is going to be the third equation, which is x squared, or 4. So once again, the overall limit does not exist because 2 does not equal 4. In order for the overall limit to exist, the left and the right-sided limits have to be the same. The last part of chapter 12 has to do with continuity. We want to know if a function is continuous. Now, the easy way to say this would be that if you traced your pencil along the graph, you could trace the entire function without ever lifting my pencil. If I have to lift my pencil and move to another part, or jump, or go over to another part, okay, then it's not continuous. Okay, now it gives us three conditions. Okay, the mathematical terms are written here. F of c exists, okay, meaning that f is defined, means this first one just means there's no holes. Okay, the second one says that the left and the right-sided limits have to be the same. In other words, there's no jump. Okay, and then we also have to have the limit and the function value have to be the same. Okay, and this is also a displaced point, and we can also have no asymptotes. No displaced point and no asymptotes. If we have an asymptote, then function, the first part would fail as well. But I just want to make sure we put that in there. No holes, no jumps, no asymptotes. And to be able to graph without ever lifting your pencil. So if we look at this first example, is this continuous? And if it's not, which function does it, which one of these three conditions does it fail? First of all, can I trace the whole thing without ever lifting my pencil? No, I have to jump. This is not continuous. And if I look at it, this was an example that I showed before with the one-sided limit. The limit from the left is not the same as the limit from the right. Okay? we are defined at the point C, so the left and right side of limits are not the same. So this fails condition 2. Okay, the second example, we have a lot of problems here. If I trace here, I have to jump again, so we know this is not continuous. Let's look at just one part of the graph. Okay, if we look at this part, okay, we have a jump from here to here, which means that our left and right side of limits are not the same. So we would say fails condition 2. Okay, lots of jumps there. Right, this last part, we have 4 different ones that we can look at. This one, I can trace it, yay, with my pencil the whole time, so we say this is continuous. The second part, if I trace this, it jumps up, okay, and then down. So this is not continuous. And that's because we have a displaced point. This point is up here. So it's going to fail condition 3. You'll notice that the point is defined. The left and the right side of limits are the same, but the point and the limits are not the same. So it fails condition 3. This example down here in the bottom left-hand corner, okay, obviously this is not continuous. I can't trace it. The left side of limit and the right side of limit are not the same. That fails condition 2. Okay, and the last example here, when I trace it, I have to go over that displaced point, go down to here, so it's not continuous. We have another displaced point, so it's going to fail condition 3. I didn't show you one that failed condition 1, so I'm just going to show you one real quick. That's if we would just have a hole in the graph. This is not continuous, and it fails condition 1. So hopefully this gives you a better understanding of continuous functions and not continuous, and how to identify which condition they fail. Hopefully this gives you a good overview of the concepts learned in Chapter 12. I wish you the best of luck on your Chapter 12 test, as well as your semester exam. Have a great day.